All right, so let's look at this is the discussion question from module number 8. So what I've given you here is this is a graph of function f, and I want to do two different things here, or start off with doing a couple different things here. The first is to make a graph of f prime. So if this is f, I want to draw a derivative of this graph using this. So lots of ways to start with this. One of the ways that I think is best to go here is that what does f prime tell me about f? So among other things, f prime tells me where f is going to be increasing, decreasing, or doing neither. So I like to start with where it's critical. Like I want to find those critical points because I think those are easiest to identify from a graph. You might disagree. You like I said, you might start this a totally different way, but I'm going to go ahead and identify those places where I think are critical points. And graphically speaking, what does a critical point look like? A critical point is where I have a horizontal tangent line, or where the slope of the tangent line is 0, or at a maximum or a minimum. So I think those points are going to be here and here. So if that is a local max and a local min for my function f, then what are those points going to look like on my derivative f prime? Those are going to be places where f prime is equal to 0. So I've only found a couple of points, but I think they're really important points to find because what this tells me is that basically my function is neither increasing or decreasing at those 2 points. So kind of implicit in that is that my function has to be increasing or decreasing everywhere else. Unless I've missed some of these extreme points, which I don't believe I have. I think I just have these 2 points. So what's happening between those 2 points? Is the function increasing or decreasing? And I can see that it's decreasing. So it's decreasing the entire time here. So what does that mean for the derivative? If function f is decreasing, I'll kind of make some notes here. F decreasing is equivalent to f prime being a negative number. So when I graph f prime here, I'm going to do it like this. I know that my derivative has to be 0 at each of these points. And because my function's decreasing between them, I feel pretty good in saying that the derivative has to be negative the entire time there. Okay, so now that I know what's going on between those 2 points, let's figure out what's going on kind of on the outside. So what's going on to the left of this first, this first critical point? So it looks like my function is increasing throughout that whole interval. So from x equals -2 up to this looks like x equals maybe a quarter, whatever this critical point is. So another thing I can say is this: if f is increasing, that's equivalent to f prime being a positive value. I'm not going to really worry about what the exact values of these slopes and tangent lines are, but what I know is this: when I'm close to this critical point, my slopes are really shallow. When I get further away, the slopes get a lot steeper. So that suggests to me that at -2, my slope is going to start off really, significantly positive, and it's going to decrease until it reaches this critical point at 0. So one of the things to say here is that everything I've ever drawn for you or any other class I've ever taken has been pretty bad, and that's okay. I mean, this sketch here is not, it's not meant to be museum quality. It's meant to be to make you think about the math that we're doing. So if I were to actually graph the derivative, it would, not look as choppy as this, but the biggest things that you can pay attention to are, for making this first derivative graph, where's the derivative 0? Where is it positive? Where is it negative? So I believe it's positive to the left of that first critical point. And I think it's also positive to the right of this second critical point for the same reasons. So after this x, so to the right of this x, my function's increasing. If I were to draw tangent lines in here, these would each have positive slopes. Not only are they positive, they are getting greater as I move from left to right. So because of that, I believe I can do something like this. So I think this is a good sketch of f prime. All right, so now I got f prime. So what else were we asked to do? We were asked to find f double prime. So how is f double prime related to f? So let's talk about how any derivative is related to the function that it comes from. So a derivative tells you, basically, if you have a function, then the derivative of that function will tell you the instantaneous rate of change of that parent function, that original function, with respect to x or whatever your independent variable is, for any value of x that you want to plug in there. That is the same relationship that f double prime has to f prime. So, a derivative will always tell you about the instantaneous rate of change or the slopes of tangent lines of the function it came from. So I'll give you an extreme case here. What if I had some function f and I had the 36th derivative of f? So it's really, really hard to think about how f is related to f to the 36th derivative of f. But let's say I took the derivative of f and I got f, 37 prime, the 37th derivative of f. I have a very good idea of how these are related to each other, because the 37th derivative is, in effect, the first derivative of the 36th derivative. So basically, this tells me about the instantaneous rates of change of this. So I'm not going to make you take that many derivatives, but I bring that up to say this. If I want to know about making the graph of f double prime, now what I'm doing is I'm going to construct that from f prime in I'm saying very much the same way, but really it's going to be exactly the same way. So what did I do to make f prime from f? I found the places on f prime, I found the places on f which were maxima and minima, and I realized that those were going to be critical points. So now I can do the same thing with the graph of f prime that I made. Looks like I only have one critical point. So that means that is going to be a zero crossing. Now that's going to be where my derivative of f prime is equal to 0. So now let's kind of use that point to break the rest of this question up into, left of that point and right of that point. So what's happening to the left of that point? So again, I'm looking at f prime here, which I've already labeled to the right, but I'll label it again. What's happening on f prime to the left of that critical point? Well, it's decreasing. So what does that mean about my values of f double prime? So let's make another chart here. What does it mean if f prime is decreasing? Well, that means that f prime is a negative value. And on the other hand, if f prime is increasing, that means that f prime is positive. So if you'll notice here, like these two ideas here are very similar to these. In fact, the ideas are the same. The only thing that's changed here is the names of these functions. But I'm still relating some function to its first derivative. In this top box, the function, the original function is f, and in this bottom box, the original function is f prime. But the first derivative tells me the same thing about that upper function. So back to drawing our graph, I know that this function is decreasing. So what does that mean about the derivative? Well, it's going to be negative. And Don't know exactly what that looks like, but all I know is that it's going to be negative. And what else do I know? Actually, that's not all I know. I can see that as I move from left to right, the slopes are getting really negative, less negative, less negative until they eventually reach zero. So because of that, the further left I am, the more negative my values are going to be. Now, by a very similar line of reasoning, as I move to the right, I can see that my slopes are increasing. So I'm going to continue this linear trajectory here. I wasn't going to draw an arrow, but I really only defined this function for a little while. So this, straight line right here, this is f double prime. So again, one thing I alluded to before were like the 36 derivative and all the stuff I was playing with there. It's much harder to think about how a function and some higher order derivative are related to each other, as opposed to thinking about how a function is related to its first derivative. That's a much simpler question to ask. Not a simple question to ask, but it's simpler than that other alternative. So when you're doing, tasks like this, it's usually best, especially now that we're right now as we're just getting started, to kind of step through it step by step. Don't jump from F to F double prime. That's a tall order. A much more manageable thing is to go from F to F prime and then to F double prime. So I believe we have our graphs. And we also asked about, and the other questions I asked in the discussion question, I've kind of talked about those organically, but I'll bring them up now. I asked you where maxima and minima were. So here is a local max. And here is a local min. Now, what derivative tells me about local maxima and local minima? Those come from the first derivative. So what is the value of the first derivative at a local max and a local min? They have to be zero. So we got that. And in fact, that's how we made, that was kind of how we started making this graph for F prime. So it's not enough. So if you find that your first derivative is equal to zero, that is not enough to say that you have a local max or a local min. In fact, it could be neither. What else do you need to do? Well, you have a couple of different things you could do, and I'll talk about them both here. Think back to optimization, which we just did in a recent module. If you found a critical point, how do you know if your critical point is a max or a min? Well, we have two different tests for that. One is the first derivative test. Let's do the first derivative test. So here's a critical point. I know it's a peak. I know it's a max because I'm looking at a graph. But how do you identify these things with the first derivative? Well, if the first derivative goes from positive to 0 to negative in that neighborhood, you have a local max. And we do. Our first derivative bears that out. How does the second derivative test work? Well, if you have a critical point and your second derivative is negative, that means you have a maximum. So look at our second derivative at that point. That also matches up. We have a critical point because our first derivative is 0, and we have our first derivative is 0, and our second derivative is less than 0, which means that we have a local maximum. Kind of the opposite of all that reasoning I can use to find or to verify this is a local minimum. I have a critical point, so the derivative is equal to 0, f prime is equal to 0, but slightly to the left of that critical point, f prime is negative, and slightly to the right of that point, f prime is positive. So that's the first derivative test telling us we have a minimum. But we also have the second derivative being positive at a critical point. That also tells us we have a minimum. So we're kind of seeing graphically now how the first and second derivative tests shake out. And I think the last thing I asked you about was where this thing is concave up and concave down. So what tells us about the concavity of a function? So the way you talk about a concavity of a function is through the second derivative. So let's look at f double prime, which is this straight line that goes from bottom left to top right. you have an inflection point. So we should talk about inflection points first. An inflection point is where your function goes from concave, either concave up to concave down, or vice versa. Equivalently, so let's do another equivalency here. F is concave down. That's equivalent to this. F double prime is less than 0. F is concave up. That's equivalent to F double prime being positive. So let's look at where our second derivative is negative. Basically, that's going to happen everywhere to the left of this point here. So second derivative is negative. What does that mean about my function f? Well, that means if I look at my function from left to right, then the slopes are, as I progress from left to right, my slopes are they're decreasing. So here I have a very steep positive slope. Go a little further right, I have a slope that's still positive, but not quite as severe. Up here, I have a slope that's, getting even more shallow. And then somewhere in here, I have slopes that are even negative. So I think all throughout there, I have concave down. Until I reach this point, when it looks like the slopes of my original function f are starting, they're starting to, metaphorically speaking, rebound. They're starting to increase from this point on. And that also matches with the inflection point, or where my second derivative equals 0, because my second derivative has become positive now. So we'll talk a lot more about this. Think about how difficult it was to kind of think about how the first derivative and a function are related. And from what I can tell, you're all getting better at realizing that. This is another layer and another function to keep track of. So it'll be very, very, potentially very difficult at first, but we'll keep fighting with it. And yeah, let me know if you ever need to talk it over.